So it's visible, right?
Yes, yes,
Okay. So shall I start?
yes, we can start.
Okay. So this is the last lecture. So far, what we have learned, uh, some different aspects of effective field theory. For example, in the bottom-up approach, if you have the information about the low energy symmetry and the particle content, and then using the symmetry principle, using the Hilbert series method, we have seen how to construct the effective Lagrangian. And similarly, there's a complementary method, which is the top-down approach. And in this top-down approach, we start with our favorite beyond standard model theory, and we expect that scale of this UV theory or the mass of these heavy particles, the non-standard model particles, are much higher than the electric scale. So we should be able to integrate them successfully, and then we can generate this effective Lagrangian at the lower stage. Also, we've seen, yes, there's a question. Okay. So then, what we have learned further, that from the experimental side, if we come to know that there one or multiple operators who shows kind of a who shows kind of a excess in the data, or this anomaly in the data can be explained by some set of operators, then instead of having a blind hunch for the new physics theories, there is a symmetry guiding way that we can start thinking of what are the minimal way we can extend the standard model, such that with those kind of extended scenarios, we can again integrate them out and get back those operators. And then we use this top-down, bottom-up approach and all these things in the context of phenomenology. And there we have noted that, okay, how the couplings and the spectrums are affected or more, or they are deformed by the presence of the effective operators, right? And then we expect, we have seen with the dimension 6 one, but certainly one can extend for any other dimension and so on. And then we have actually make a comparative analysis that even for a particular theory, whether it's a top-down or approach, the same operators, if we assume to be in a bottom-up approach, then what are the different signatures on them? Why this bottom-up approach give you always the overestimated thing? How these theoretical correlations are missed out in the bottom-up approach, and how that is grabbed in a top-down one, and why it's difficult to translate or use the fitted data in a bottom-up approach directly into your to understand the BSM parameter space, and also how the EFT can be a very useful tool to understand and the preferable models in the light of different kind of LHC data. So these are the more or less things that we have learned so far. So now, today we'll try to deviate from that, and we'll instead of SMET, we'll talk about much more low energy, which is the low energy effective field theory. And very briefly, I'll just touch upon that thing, that if you start with the low energy effective field theory, how that gives you the sense of the UV models and going to the via SMET kind of scenarios. So this is the low energy effective field theory. So when I'm saying the low energy effective field theory, you basically have all the light quarks apart from the top and also the gauge bosons, Higgs, and all those things are integrated out. Your symmetric group is AC3 colored times C1 electromagnetism because you have performed the electric symmetry breaking, and BL numbers are basically accidental symmetry. Your space-time symmetry is still the Lorentz group, okay? And then what you can actually see here, that if you start with some interesting observers, which you have not observed yet, but you can certainly design them based on your theoretical thing, and then try to get an idea that, okay, what kind of UV scenarios can lead to those kind of phenomena. So this is a kind of an application, a different kind of application of unfolding of the operator, you may think on that way, right? So for example, you can think of an analogy like proton is decaying. You know, the proton is considered to be fundamental, not fundamental, but stable particle. It can have a very different kind of decay modes with different kind of lifetime. So these are some interesting channels are there. Proton going to two charged lepton, one neutron, and one charged kaon. And another case, proton is decaying to three charged leptons. Certainly, you can see there's a these decays are possible only when you allow the baryon and lepton of parting interactions, right? So this kind of, for example, this process can be mediated at the low energy effective field theory, which is dictated by these six fermion fields are there. So this is like a dimension 9 operator, dimension 9 operator, and then if you see that at the standard model effective field theory level, this also can have a psi to the power 6 operator, right? But only difference is that these quantum numbers in the parentheses are given in terms of low energy effective field theory. So it is dictated by this quantum number. So one has to be careful that how these quantum numbers are embedded in the standard model gauge symmetry. So that's how the parentheses quantum number are modified and appropriate to the SMAP context. Okay, but you see the operators are basically similar, but their quantum number of the fields are now different. So if you start with this SMAP operator, once you perform the electric symmetry breaking, you basically get this operator again. The same dimension 6 operator, same class, but the quantum numbers of the fields are basically different. That's the only difference here. But then you can unfold this, vertex, effective vertex, and then you can inject different kind of scalar fields. Okay, and this is one of the possibility you can find out that if you add, color, two color scalar and one two Higgs doublet kind of thing, addition Higgs doublet kind of thing, and then you can have a BSM scenario where you have these external states which are basically your standard model fermions, and in the intermediate state you have these UV particles are there. So this is the UV scenario you can think of, and then in this UV theory, if you have given Lagrangian, you can write down looking at the vertex, okay, and then in that model actually you can have a proton decay which is basically led to this kind of decay channel. And this proton decay lifetime will certainly depend on the mass of these heavy particles and these three different kind of equal couplings and the scalar trilinear kind of couplings here, right? So now this Wilson coefficient associated with this dimension 6 kind of, dimension 9 kind of operators, okay? And that is actually a function of this parameter. So from the exclusion limit, because you have not observed so far this kind of decay, there is a stringent limit on the lifetime of the proton, and which you can translate into their partial decay width, and you can see that if you have a limit on that, that will certainly limit the coupling and the masses of this kind of new particles. Okay. And another interesting example is basically proton going to this, three charge electrons, which is a very interesting channel, because there is no neutron associated with this thing. So this is much more cleaner, I would say. And there you have not only 6 fermions, but there's a wave involved in this process. And that wave is basically replaced by a scalar field when you talk about in the context SMAP, because SMAP, this is before the electric symmetry. So the wave is replaced by the scalar doublet here. And similarly, when you unfurl this vertex, then you may see that, okay, so there's a red color, these heavy particles you introduce, which are non-standard model particles, okay? And once you integrate them out, you basically get this operator. So this tells you that the way we are talking about the observation, observed quantities, which you can parameterize in terms of SMAP operators, and then you try to unfold them and try to understand what kind of UV theories can give us the explanation for the excess of those kind of data. But also you can look into some rare processes and you can find out some kind of new interesting signatures you can propose. And not only that, and then based on the effective field theory, unfolding the operator, you can really think of what are the minimal extensions of the standard model which actually lead to those kind of interesting signatures. So now this is another networking. You can see that this tells you basically there's a different class of operators in the SMAP level. Okay, starting from 6 to 9, and in the left in the low energy effective field theory, just dimension 5 to 7, and this gives you a basically nice tracking. And that okay, so which class of SMAP goes to which class of low energy effective field theory, and how the representations or the baryon number lepton number violations of this kind of operators if you invoke, okay, and that will lead to similar kind of baryon lepton violation in the low energy effective field theory. So this is like a tracker one can use to going from understand the low energy effective field theory and their possible embedding in the SNAP. So, but this is a very primitive, I would say, because here the this tracking it has not been considered that how the standard fields are integrated out, okay, or their loop contours and so on. But this is a start to start with. This kind of tracking is always a good guideline. Okay, so this is one of the things I wanted to discuss actually. Okay, yeah. So any question up to this point? Fine. So now, so far, what are the discussions and the examples I have talked about is basically up to dimension 6. So now we'll try to look beyond dimension 6 and then see what are the interesting phenomena that could arise. And also from the methodological point of view, the lesson that we have learned and the methodologies that we have developed to compute the dimension 6 effective action, whether they are equally useful or we have to be careful something else if we think about beyond dimension 6. Because dimension 8 is also important and for various reasons, and we'll try to hint upon some of the aspect there also. So that's the idea. Basically, the question we start with, is dimension 6 sufficient? And why, what are the beyond dimension 6, like dimension 7, dimension 8, and all those things, so we have to truncate them. And most importantly, if we think that beyond dimension is important, the next question would arise, okay, if it's important, and then what are the beyond dimension 6 structures, right? So let's try to understand, is dimension sufficient? So now, when you come with a from the top-down approach, okay, then we are integrating out the heavy fields. But if you recall my earlier statement, that top-down approach effective field theory is very similar to an effective approach to calculate the full theory. That means basically, if you can calculate the effective field theory in a more precise way beyond dimension 6, that will give you much more closer view of the full theory. Okay, so that's why I mean it's important for the top-down approach, unless you are very sure and then see the error that you are doing without not considering beyond dimension 6 is much lesser than the resolution of the data, then you are safe. But if it is not, then of course one should include the dimension 8 operators. Another interesting question, basically the decoupling. Now, what is this decoupling? Instead of having a very formal definition, that we can think of the decoupling is you consider some low energy theory. Yes.
Yeah, so the statement that you made about that this top-down approach, and I think this you're saying this dimension 8 operators, let's say going beyond dimension 6 might be better because you can pin down them more, or maybe pin down the effect more efficiently, right? That's what.
Yes, because you will be considering more contribution to the observables without changing the degree of freedom. Yes.
Okay. Without changing the
number of independent parameters.
Number of independent parameters. Okay. Okay. In case of bottom-up approach, you have the
bottom-up approach, you can
introduce few additional parameters. So it will
yes, because because if you add more and more dimension 8 operators beyond dimension 6, all are independent and treated as a free parameter. So there's a comparison between gain versus loss to the number of parameters, right?
Yeah, you introduce some again some
exactly. Parameters. So that's why I mean it's very unlikely, but sometimes you have to do, because some of the observers have a contribution directly from dimension 8. No dimension 6 contributions are there. In that particular cases, you have to add dimension 8. Yeah, so I'll comment on that aspect later.
Okay.
Okay, great. Any other question?
So what if we like insert 2 dimension 6 operator inside a loop instead of like contributing 1 dimension 8 operator?
No, the question basically is not about the 1 or 2. The concept is basically where you are truncating the Lagrangian. Okay. So if you are truncating your Lagrangian dimension 8, okay, then it's not about the dimension 8. You have to calculate dimension 6 also. And then 2 dimension 6 operator from 2 different vertices will give you an equal contribution to dimension 8. So dimension 8 is equivalent to a linear in dimension 8 plus dimension 6 square.
But our number of parameter will be lesser if I like introduce 2 dimension 6 parameter instead of dimension 6 plus dimension 8 operator.
No, the question is basically you cannot create your own principle of analysis, right? You have to follow the field theory. So if you are adding a 2 dimension 6 operator, you are actually enlarging your analysis up to 1 by lambda 4. Then I don't find any good reason that you will leave out dimension 8. That I would call a very abruptness in the calculation. That is not a good thing to do in the quantum field theory.
But then the dimension, if you introduce dimension 8, the logic will be good anyway, going also beyond, let's say, 1 over lambda to the power 4 also, right?
No, no. The question basically, if you are adding a 2 dimension 6 in the vertex, that is
oh, 2 dimension 6 in a same diagram or same vertex.
Yeah, that's what he is asking actually.
Oh, achha.
Like
That means
like
basically
one loop, but
I
the
think
2
he was
dimensions.
asking also number of parameter. I think the number of parameter will be, if you introduce 2 dimension 6, you have two independent parameters there as well if you're doing bottom-up approach.
No, in the bottom-up approach, let's say you have a 2 operators, right? 2 O1 and O2 you are introducing. Okay. So
2 dimension 6. You have two parameters also associated.
Yeah, so 2 dimension 6 means basically in the bottom-up approach, 2 operators means 2 parameters. One.
Exactly. And
right?
1 dimension 6 and 1 dimension 8 also introduces 2 parameters.
No, yeah, but the point is basically if you add, so I think the question is basically instead of adding a dimension 8, I can take a 2 dimension 6 square kind of contribution. Each dimension 6 coming from individual vertices or in the loop actually, I'm sorry, right? But actually you are calculating up to order 1 by lambda 4. Then you have to justify the reason that why you are not considering all 1 by lambda 4 contribution.
Yeah, that's true. But I don't know whether his question was, what was his question?
Like like inside a loop, if there is a 2 vertex and each vertex insert the 2 dimension 6 in each vertex, then instead of like inserting 1 dimension 8 in one vertex and another is standard model, if I put like 2 dimension 6 in the 2 different vertex, then
no, that's what I'm saying. It's in field theory doesn't go with your choice. That's not my point. My point is basically if you add 2 dimension 6, you are allowing your theory to calculate 1 by lambda to the 4. If you are allowing your theory to 1 by lambda to the 4, you have to add all the operators up to 1 by lambda to the 4.
Yeah.
For example,
yeah.
left-right symmetry, for example, left-right symmetry model has a huge potential structure, the scalar potential, right? But that will spoil many predictions. But it is not in our hand that I just chop off some of the operators. That's a bad quantum field theory, I would say. So symmetry allowed term, or wherever you are truncating, you have to allow all of them. If you're adding you are considering a 2 dimension 6 contribution, you have to add a dimension 8. Otherwise, there will be problem with the renormalizability also.
Sometimes may not also have gauge invariance or other things, for example.
Sorry?
And sometimes you also may lose gauge invariance and other things because, as you said, right? For example, the photon mass thing.
Yeah. For example, if you have 2 dimension 6 operator and if you take the calculate the quantum corrections, you will get a counter term which will give you a dimension 8 operator. Then how to cancel the divergence? You cannot cancel. I mean, that's why if you see that unless you add a dimension 8 operator, you cannot cancel the divergences coming from insertion of the 2 dimension 6 operators. You suffer from the divergences. You have to renormalize the theory properly. And if you see in the literature, the dimension 8, though the results are very small, the dimension 8, I would say dimension 8, what should I say? Dimension 8 anomalous dimension matrix, it is not only getting the contribution from dimension 8, but also there's a contribution from dimension 6 square. So they are related, they are not completely independent. So yeah, I can understand because most of the literature are very blind and use those kind of things without understanding much effective field theory. So that's why their erroneous results are there, in the literature. Okay, so coming back to the question of the decoupling is that when I have the standard model, the low energy theory, right? And then, so if I add a new particle, okay, fine, they're interacting with the standard model part. Now the question is basically, okay, so if I want to integrate them out, now the question is really, you have the tools to integrate out, doesn't mean that you can always integrate that out in a consistent way, right? So that's what the decoupling theorem tells you, that your theory needs to be in the decoupling regime. What does it mean? That means basically this theory is not very strongly coupled. Now, when the theory couples, for example, just think the simplest way. Let me give you one example of that. When you add a scalar field and that scalar mixed with the standard model Higgs, so now in the extended mass matrix, there will be mixing and so on, right? So your physical state of the standard model Higgs contain a mixture of some BSM scalar as well. Now, if it is the case, then the Higgs data and all those things are basically have to be consistent, such that the mixing and all those things are permissible. So now, what are the parameters involved here? There's one case, it could from the tilinear coupling, it can have a dimension, full coupling, or there's another coupling which is basically mixing angle, which is dimensionless coupling. So now what you can do, you can imagine a situation where this mixing angle is tends to 0, okay, and this mass of the heavy particle is tends to infinity. So that's basically two boundary you are considering. In one case, you set the mixing angle to very, very small, and the mass of the heavy particle is very, very large. In that scenario, the theory is really decoupled from the standard model, and the new sector is really decoupled from the standard model. But this is a very idealistic situation, because in these particular cases, you wouldn't expect anything in the observable from this new sector. So the question is basically, if I want to have a reasonable amount of impact from this new sector, but still I can use the EFT, okay, so then we have to make the balance of this decoupling. So we have to design this idealistic decoupling to a realistic decoupling one. Now, what is this case? The case is basically now what you do, you start the mixing angle making from 0 to some finite value, and the large mass of the heavy particle, which you have set to be infinitely large, you make them try to finite. So you basically approach it towards each other, and then you try to check at which boundary the EFT truncation actually works. That means the contribution from dimension 6 will be always larger than the dimension 8, but the dimension 8 could be important. Now, where to truncate and all those things, this is like a philosophical statement, okay? But how to estimate, and that estimation should go case by case. That depends on what is the new particle, what are the quantum numbers, how it interacts with the standard model, and so on. So those detailed features actually decide where to perform, where to keep the mass of the heavy particle, the minimum mass of the heavy particle, it can be larger than that, or how much mixing you can allow. Still, you can perform the effective field fitting. Okay, so now you can see that I may have used the heavy scalar to be, let's say, 1.5 TeV, okay, up to dimension 6 truncation. But I can really calculate dimension 8 or dimension 10 order of my contributions, and then I may find out I don't need to keep this lambda or the heavy particles mass to 1.5 TeV, rather I can bring that down to 1 TeV or 800 GeV. Okay, so that's how where to truncate. Based on that, the choice of the cutoff scale may vary. And not on top of that, there's another effect from the RG. So where you put in the cutoff, okay, and then you perform the RG, so RG will mix the operators, and that can give a significant effect to understand the decoupling of those kind of scenarios. So we'll see one example with that. So the first question that we should ask, that if we have to go beyond dimension 6, then tree level we know, because this is exactly the similar thing that we have learned from the dimension 6, that you have the heavy field, okay, you expand the propagator of the heavy interacting propagator, and there you find out the classical solutions. You keep some order of more terms to calculate dimension 8, okay, you plug in back in the Lagrangian, you get dimension 8 contributions. But as I told earlier, that on that when you have this dimension 8 contribution, we will have two contributions. One is directly integrating out, you get directly the dimension 8 operators, but also you have this effective action up to dimension 6. If you focus on, there will be lots of redundancies. And these redundancies are due to the equation of motion you have not imposed yet. So what you have to do to remove the redundancies, now impose the equation of motion of this Lagrangian up to dimension 6. So this is the difference. When you truncate into dimension 6, then you use the equation of motion up to dimension 4. But now you are extending your set of operators up to dimension 8. So you have to use the equation of motion of dimension 6 effective action and plug in back in that Lagrangian. So then what will happen? The dimension 6 redundant part will give you some dimension 8 contribution. But those dimension 8 contributions will be in the size of dimension 6 square. Okay, so that's how dimension 8 got actually tree-level 2 contribution. One is directly contributing, directly integrating out, which is linear in dimension 8 operator, and there's another contribution from the equation of motion in dimension 6, which is the quadratic in the dimension 6. Okay, but
So
there's
you
a
said
catch.
last time,
Yes.
you said last time that, for example, when I am using dimension 6 operator, I should in principle use equation of motion up to dimension 5, right?
No, dimension 5, but in the standard model effective field theory, we know the dimension 5
Yeah.
basically left now violating thing. So that's why I'm not considering dimension 5 here.
Okay. But in general, it should
In
be
general,
less
yes.
than
In general, absolutely correct. In general, yes. Yeah. But there's another catch. The catch is basically there's a why we use the dimension 6 to filter, because dimension 6 is equivalent, we serve the similar job as the field redefinitions. Now, what is the meaning of the field redefinitions? That okay, so you have an effective Lagrangian, and then you can redefine your field by phi as a phi plus some function of phi or some other fields times phi. Okay, so this is the redefinition of the field. So if you redefine your field and use the redefined field in your Lagrangian, then it will remove the redundancies. Okay, so that's why the redefinition of the quantum field is basically very important aspect. And it has shown the redefinition of the field is actually equivalent to equation of motion or vice versa. But now, when you go beyond dimension 6, field redefinition is the fundamental thing to do, and it works absolutely fine. But equation of motion, the simple Euler-Lagrangian equation of motion, if you use, then you will find out that some of the contributions are missing out. There's a mismatch between the equation of motion contribution and the field definitions. So that's why one has to modify the equation of motion, and that is equivalent to something like a quantum equation of motion. One has to introduce, and that I'll show how to do that too. Okay, and now you might be asking, okay, if I know the field definitions, then why do I need to go for the equation of motion? The reason is basically, field definition one has to do case by case. Okay, but equation of motion is much more have an algorithmic power. So that's why when you design a program, automated program, there it is suggested, it is easy to implement equation of motion rather than the field definitions. So from a realistic, methodological purpose, equation of motion, one has to focus on that, and that's why one has to work with the modified equation of motion.
Okay.
So now let me give you the chalk out plan to how to get this dimension at the tree level. You start with, let's say, standard model plus heavy scalar. You integrate out the heavy scalar. So if you go for using the codec, that okay, you have a dimension 6 operators, and dimension 6 operators, you can have first non-redundant structure, and then equation of motion you can use, and then you get from redundant to non-redundant, right? And from the tree level, if you focus, you get the dimension 8 operators, and there you first get the redundant structures, and using the equation of motion, you get the non-redundant structure. That's why when you integrate out, you get effective action of dimension 6, dimension 8, and this order. So these are two independent parts. So, but now in this redundant structure, when I'm using the equation of motion of fields up to dimension 5, then or dimension, if you forget that variable number left of operation, just think of dimension 4, then I get a non-redundant dimension 6 operators. But if I use the equation of motion of dimension 6 up to dimension 6 Lagrangian into the redundant structures, then I got basically dimension 8 contributions. But that is not the normal equation of motion. On top of that, one has to add this additional part in the equation of motion. So equation of motion plus this term. And I'm not going to prove this thing, but there's some existing literature there that how this modified equation of motion pops out this term, and doing this equation of motion with this modified term in the equation of Lagrangian equation, you'll find out this is exactly same result you'll find out if you do the field definitions. So in this way, at the tree level, you can integrate out and grab that both the contributions to the dimension 8.
Jodi,
Yes.
will it be possible to elaborate this little bit more?
This one?
Yeah.
Okay, so you can think of, like as I was telling, the field definitions works as a like h going to h plus h dagger h times h, right? And this gives a very similar kind of structure here actually. Okay, so then so what you do, you want because the redundant structures, what I'm saying, they're actually having a higher derivative operators. So once you have the higher derivative operators, then one has to use the most generic Lagrangian equation where the higher derivative operators are there. Okay, and if you include that higher derivative operators involved equation of motion, then you get this term. Yeah, that's it.
What do you mean by second order equation of motion now?
Because
higher derivative.
Yeah, basically, if you see, we generally use the del L del phi minus del mu del L del mu phi, right? But now, if you have a d2 phi, d3 phi, those kind of terms, then one has to have some. So if you look into the generic Lagrangian equation of motion, that is not truncated at del mu. It's a del mu, del nu, del mu, del nu, del rho, and so on. Higher terms are there. So one has to take care about those terms also in the equation of motion.
Okay.
So the generic Lagrangian equation of motion one has to use. Okay, because that even it's a very simplest example one can see that in the irreversible scalar field theory, generally we write down we calculate the equation of motion considering d mu phi Lagrangian. But let's not consider that Lagrangian. Consider minus phi dagger box phi, and then you find out the equation of motion. You have to see. You have to go beyond d mu. So, similarly, it's very similar to that. Okay. Yeah. Exactly. Okay. Any other question?
Thank you.
Okay. So now, once you have the dimension 8 operator, so if you remember the way we classify those models based on different kind of observers, capturing the effects from different kind of dimension 6 operators. Okay, so here also we can see that what are the dimension 8 contribution to those observers. So now, along with the electric equation data and the Higgs signal strength, we have added the VBS, vector boson scattering. But it doesn't mean that vector boson scattering doesn't have the contribution to dimension 6. Of course, they have, but I have not included there. Okay, but on top of this, which is not included, or maybe it's like a encapsulated within the VBS. What is important is the neutral trilinear and neutral quartic gauge coupling. These two observers are not getting contribution from the dimension 6. The leading contribution of the effective field theory they got from the dimension 8. Now you see, if you have a nice measurement in that channels, okay, then of course, if there's an excess, you must take on board the dimension 8 operators, otherwise you cannot explain. That tells you one of the important motivation to look for beyond dimension 6. Okay, so now if you see this light green is basically for the electric vision observers, and the Higgs signal strength is this, and this is the VBS. And these are different kind of dimension 8 operators participating in this quantity. And now you can see that if I take on board all these quantities, then the way I demonstrate the breaking the degeneracy among the different models based on the data. Similarly, dimension 8 level also you can perform the similar analysis, and that tells you what is the status of the degeneracy of this in this theoretical space based on the dimension 8. Now you think you blend this together, dimension 6 and dimension 8 contributions and more observers in terms of VBS and neutral gauge couplings. Okay, so that's a possibility that one can possibly improve the situation from the dimension 6, and that's a good motivation for the dimension 8 apart from the precision results. Okay, any other question up to this part? Fine. So then about the decoupling, what I was talking about, let me demonstrate how these things can work here. So what we do, we try to focus on the simplest, observable, which is the oblique parameters. As you know, they are basically STU, the 3 oblique parameters are there, and they are being computed from the 2-point function of the gauge fields. So you basically calculate the pi mu, right? And then apart from the standard contributions, you only focus on the effective contributions, because that's the deviation you would expect. And if you calculate the STU, you will get in terms of unphysical in the unphysical basis, but always you can diagonalize them and go to the physical basis and so on. So yeah, so this is the one of the snap case you can calculate. For example, you have the modified gauge fields and the scalar field. If you recall how the spectrum was modified, then you understand which operators contribute there. And on top of that, you have this 5, 4, D2 and 5 square square operators. If you add them, your W sector get modification in the bilinear structure like this, because I am focusing on the bilinear structures, because that's for the 2-point function will get the contribution, right? And similarly from there, I can calculate the pi mu, and if I use the definition of STU, I'll get this contribution. And the U is basically here 0, because I'm truncating at the dimension 6. As you know, there is no contribution from dimension 8 to S and T. And so if I do not include any kind of, dimension 6 contributions are only to S and T, there is no contribution to U from the dimension 6. The U gets contribution only starting from the dimension 8 level. Okay, so if you want to do dimension 8, then of course you have to input this effect, but this is for the dimension 6, so this is the situation. Now, what we have done, basically, we have considered simplest. This is just for the purpose of demonstration. So you include basically the standard mode plus heavy singlet scalar, and then this is the trilinear coupling, and this is the mixing angle that you are allowing. Actually, you can see that cos theta is the larger value, implies basically, basically the mixing is very, very small, because cos 0 is 1, so cos theta larger value is going to very, very small region. Now we want to see what is the competition between the heavy scale involved in the theory versus the mixing angle. Okay, and then you can see that if I choose those scales to be defined 1 dB, 400 GB, and 150 GB, and these are the defined mixing angles consistent with this value of the eta s and ms, then you'll see that the deviation, what we calculate from the full theory and EFT, while considering up to dimension 8 contributions, you'll see that that deviation actually reduces again and again when you go for actually the smaller value of the eta s. That means basically you keep the large mass to be 1 dB, but your eta s is basically the mixing parameter with this thing. Then even your cos theta is larger value, but because the eta is smaller, it talks less to this dimension full coupling, and that's why the higher order corrections in the EFT are less important. Okay, and if it's less important, that means if I truncate of dimension 6 or dimension 8, that will be sufficient and equivalently replaced by the full theory calculation. That's why it shows this trend actually. And a similar game is played for the in the context of the defined order of the perturbation. For example, if I consider dimension 6 only and without doing any kind of RG and so, then I can see there's a significant deviation, okay, for the lighter masses, I would say, with the full theory and the EFT. But this deviation actually reduces once you include dimension 8 contribution. And as I told you, if I include dimension 8, then obviously I have to include the dimension 6 square, because otherwise I will be missing out some intermediate contribution. And then on top of that, there's some RG contribution of this operator. And then you see that if I go for higher and higher, and then basically there are lesser deviation from the full theory. And once you incorporate more contribution in the perturbation series, then also compared to the D6 corrections, they will give you the less deviation this thing. So that's why this is quite expected, and that can be visualized from this chart kind of plot. Yeah. Any question of this part? Okay. Fine. So now
there is a similar plot for deviation in U parameter due to dimension 8 only.
U parameter we could have calculated. I think it's maybe in the paper. I can't recall. But yeah, but that will not change the pattern. So that's why we said okay, because I have to compare from dimension 6 and dimension 8, because U there is no dimension 6 contribution, so I cannot really compare.
Yeah.
Yeah.
It will be slightly different from this, right? The dimension 6 will not be there.
Yes, dimension, so only that there's no other candidate to compare with. So I can calculate only dimension 8 contribution there.
Okay.
Yeah. But the error bars are so large that I do not expect them to be beyond that. So I'm not worried about that part.
Okay.
Yeah. Any other question? Okay. So now, so we have gathered a little bit of idea and the sense that why dimension 8 could be important, why and where they're important, how to calculate dimension 8, using the tree level. So now the question basically, what about the dimension 8 one loop effective action? That's what we need to compute. So that's why we take on board a new method to do that thing, because function method we have tried and many people have tried, but that actually give you not very I said less tedious one. So that's why it's almost impossible to calculate the dimension 8 or beyond dimension 6 with the function method. And that's why we come up with that hit kernel method. That's why, what is that? That's the simplest one, though I cannot describe every details about that thing, but I think it's a good idea through this lecture series to get an idea that what are the modern tools people are using, and if you're interested, then you can dig out them. So what we are doing, basically we are focusing this Lagrangian, and Lagrangian written in this particular form, where phi is the heavy field, okay? And now you see inside this phi, there's an operator sandwich between them, which is a delta operator. Now what is this? It's the d square, the covariant derivative square, the u is the interaction term, and m square is the mass of the heavy field. U captures all the interactions, and this is Euclidized. So this d is basically, if you Laplacian, if you think of, it's like Euclidean Laplacian. So time and the space have the same signature, okay? And then the effective action you can write down in this particular format, where k is the heat kernel. Now what is the heat kernel? Heat kernel nothing but the solution of this heat equation. This delta is basically, you can think of like a Laplacian operator, and del t is not that, don't consider the time, but like a Swinger parameter. So you can see the interesting part of the heat equation, it's a linear in Swinger parameter, but it's a quadratic and in space time, okay? And this differential equation can be solved with the initial condition that k at t equal to 0 as delta x minus y. Now this heat kernel can be written in terms of decomposed in two parts. One is the free part. But the free part is basically when you set u to be 0. That's why you define as a free part. And when you switch on the u part, is basically called the interaction part. Now this decomposition is only possible for the degenerate mass or a single heavy field. Why? Because if you remember the solution of this thing, if you recall the solution of this thing, then you'll find out k is basically to the power minus delta t. Now, basically you are decomposing this delta. Delta is basically d square plus u plus m square, right? So this decomposition in the exponential, if you remember the quantum mechanics, we have learned that e to the power a plus b is e to the power a times e to the power b only when a and b commute. But if the m square is degenerate, then m square is proportional to identity. Then only it commutes with u. But if the m square is not degenerate, if a different masses of heavy fields are there, then it's not guaranteed that you commute with the u. It is diagonal, but not proportional to identity. That's why it will not commute with the u. That's why we cannot decompose in this way, and I will tell you how to do that thing. But let's start with the simplest one.
Just
Yeah.
M square.
M square. Yes. Sorry, I do not get your question.
Which m you're referring here?
M is the mass of the heavy particles.
Mass of the heavy particle, but there is only one field, or
okay, you can, if you have a one field, then of course m square and u commute. So I can write down this way. Or if you have a multiple heavy fields, all are degenerate, still m square proportional to identity, then it's commutes with u. But if you have a different masses, then it is diagonal, but not proportional to identity, then it may not commute with the u. Then I cannot decompose like this.
And this u only depends on the low energy fields.
No. This u.
Yeah, u is a function of.
Yeah, this u. Yeah, if you are working in a renormalizable UV theory, this is a function of your this thing, but it may contain also, I would say, heavy fields, because for example, phi 4 theory, capital phi 4 theory, in that case, the phi square is there. Yes.
Okay.
But dimension 6 level, if you consider, then you can assume this U to be only in function of light fields.
Okay.
Yeah.
And okay, one more thing, just
Hmm.
the two delta that you have, one is delta X, I think that is the special.
Okay. Okay. Delta X to signify that the derivative is with respect to X coordinate, not the Y.
Yeah, I'm saying, but the delta, another delta that you have inside the argument of K.
This
that
one
is, yeah, that delta
is the same delta, but because it's like a X, that's why I don't need to say it's a X.
Okay. Mhm.
Okay.
Mhm.
So you can think of this equation is like a depending on two different space time point X, Y. Okay.
Mhm.
But effective action when you calculate, as I was telling earlier also, you basically take the limit X minus Y equal to 0. That's why it's like a XX.
Mhm.
That's a coincidental point.
Mhm.
Right?
Okay.
That's why this derivative actually guided by the delta X minus Y. So whether you consider X coordinate or Y coordinate, it doesn't matter because it's accompanied by delta X minus Y.
Okay.
But here it is important to make, but these are equivalent. You can write down a delta Y also here. But then you have to perform in terms of Y coordinate system.
Okay.
No. So now one can write down in this particular format. So the important part is basically the interaction part. I can expand. And how do I expand this thing? So this quantity, if you solve the differential equation, okay, you will find out in this particular, in d dimension, this is written like this. And remember, my metric is basically all negative. So this is actually minus mod of x minus y whole square. So this is give you the Gaussian structure. Okay, so that's why in the limit x minus y tends to 0 and t tends to 0, this gives me a proper Gaussian kind of structure, the free part. And that's what it expected actually, this thing. But more important, this interaction part, what you can write down in this asymptotic form. Okay. Now the question basically here, the interaction part when I'm doing the expansion is not the Taylor expansion, it's the asymptotic expansion. And by construction, asymptotic expansion is not guaranteed by to be convergent. Then still I'm using this asymptotic expansion. The reason is basically because these are accompanied by 1 by m square kind of series. So these may not be convergent, but they are accompanied by 1 by m square, 1 by m4, and 1 by m6, and so on. So that m, which is sitting here, e to the power minus tm square, this is being used as a Gaussian regulator for me to and also guaranteed the convergence. So now once you glue that part, then effectively you can write down the effective action in this particular form. And these BKs are called the heat kernel coefficients. Okay. And this mass is the mass of the heavy particle. And you can see, very interesting to see that K equal to 3 onwards, you will get the effective operators, right? And that's what you expect. If you set 4-dimension theory, D equal to 4, K equal to 3, you get 1 by m square. So K equal to 0, 1, 2, they gives you basically the correction to the renormalizable part, because when you integrate out, you will generate some contribution to the renormalizable part. But renormalizable part contribution need have some kind of divergence associated with this for this gamma quantity. So one has to renormalize the theory again for K equal to 2, but beyond K equal to 2, starting from 3, 4, 5, 6, and so on, I get only effective operators, and those effective operators, the gamma is basically the argument is positive. So I do not have any divergence from the gamma. So that tells you directly that why in the effective operators are not associated with any kind of divergences, why they are finite. And this is what could actually expected, because I start with the renormalizable theory. So in the process, if I generate an effective operator, that must be finite. That's what we know from the power of renormalization theory, right? But anyway, now the whole game is basically to calculate the BKs, and it's a really tedious job. I mean, the 100 of pages one has to calculate to get this B's. So, but important part is that this B, when you calculate, are independent for any, are actually equally applicable for any kind of model, because these B, what you calculate, are actually function of D square and U and M square. And once you calculate those B's in particularly B1, B2, B3, B4, and so on, then you plug in back there. And what we did, now you can see how complicated the B structure is actually. Okay. So this is the full one loop effective action after dimension 8. And this is the only existing result we have computed and exist in the literature. Nobody has computed this thing so far. The dimension 6 was there earlier, but we have extended to dimension 8. And here is U, you can see that is the function derivative of the Lagrangian density from the phi I, phi j. And this is what goes into the codec. Okay, so up to dimension 6, this equation goes into the codec, and now the next target is basically to extend that for dimension 8, such that when you integrate out, then you should get the effective action up to dimension 8. Now let's try to understand some of the terms here. Let's look at the first 3 terms. These first 3 terms, you can see that basically log terms are there, and that is what expected, because these are associated with your renormalizable operators, right? And they have the finite correction in terms of log m square over mu square. And mu is that basically because we are doing this dimensional regulations, or even you do the zeta function regulations, mu is the renormalization scale associated with this, m is the mass. Now, what is this operator u? U is basically del 2L del phi 2. So u has a mass dimension 2. So now one has to be very careful here, because u can have a mass dimension 2, but inside the u, the operator dimension can be less than that. For example, u can have a term like kappa times phi, where kappa is the mass dimension full coupling. Then the operator dimension of u is basically 1, but the mass dimension of u is basically 2. So case by case, one has to understand. And what is this p mu? P mu is nothing but my okay. So P mu is basically the representative of the covariant derivative. Okay, so P mu u is basically written as a commutator of u. Okay, so P mu u commutator, and all are basically closed derivative. And G mu nu are basically the commutator of P mu, which is the field strength tensor, and J nu is given as a P nu commutator. So now, once you calculate all these quantities for a given theory, then you know what is your effective action. But of course, I mean, you can understand there's a lot of algebras will be involved with that thing. But the beautiful part is that using the heat kernel, we can give a model independent, compact action, effective action up to dimension 8. That's the beautiful part about this thing. So now, if you see, our starting point was basically this, and this reminds me of the scalar field theory, right? Now the question is basically, if I try to think of about the fermion part, then how do I do that thing? But before proceeding for fermion, I'd like to stop here and ask you if you have any question. Okay, now let's try to understand that if I have to inject the fermion, then automatically you can understand this method doesn't work. The reason is basically the mathematical property of the heat equation associated with something called the strong elliptic operator, the delta. All the eigenvalues of the delta must be positive. Okay, and that's when there is some mathematical definition of strong elliptic operator, so on. We don't go in detail, but you can see this is certainly quadratic in D2, and we can use the heat kernel method. But if you think about the Dirac equation, okay, the Dirac Lagrangian, right, and there it's a linear in D. Not only that, its eigenvalue can be plus m minus m both. It's a weak elliptic operator. I cannot use harmonic field theory for the heat kernel, but I need to massage those fermion Lagrangian, and then I can use that. How? It's a very simple thing. What you do, you use a double copy of the fermionic operator, and that's what in the literature it's called the bosonizations. If you have a fermionic theory, if you bosonize, like doubling the copy of the fermionic field theory, then you create a bosonic field theory. And when you do that, d slash plus m plus u kind of theory you have, you bosonize that, you generate d square plus u plus m square kind of bosonic action. And that's why once I bosonize that, I can rewrite the full fermionic effective action in terms of this. And then, interestingly, I can still use this formula. So though I started with a bosonic action, but I can use the similar formula for the fermionic field theory. Okay, but there's a catch. That if I am using the bosonic field theory, I have to replace some of the quantities. Because remember, here there's a trace involved in this context, because there's a, if you recall, the trace were there in this thing, and this trace is basically in the internal space. But in case of fermion, this trace not only on the internal symmetry space, but also in the Clifford space. That means the fermionic modes also should be traced out. like the trace of gamma mu, gamma nu, and all those things. One has to be careful about that part. And that's why if you replace in the formula what you have calculated for the scalar, this p mu by p mu minus I gamma phi gamma mu r, why this term is coming out, for that one has to see how the bosonization and all those things are computed. And I would suggest to look into these two, especially this paper where we have computed explicitly detailed structures. But the point that I'm going to highlight, that these variables are suitably replaced by these quantities, okay, then automatically for harmonic theory, whether it's having a self-halting coupling or pseudo-scalar coupling or a scalar coupling, you do not need to worry about. You just replace them by these quantities for the fermion, and you can still use the this effective formula to calculate the dimensionate effective action while integrating out the heavy fermions. So that is the universality about this formula, that it can equally applicable for bosonic part as well as scalar part and the fermionic part. Yeah. So any question after this part?
So the last one is this for spin one also, right? The fifth spin.
No, this is still I'm using the gauge field as a background field. So this
Okay.
d mu is still the commutator of the d mu d nu. But this is certainly field strength. But the field strength,
If you want to extend this for let's say if you want to integrate out some heavy spin one particle.
that's a good question. That we are on the process, because the problem with the gauge theory is that it's a bosonic theory is fine, but when you have a gauge theory, then one has to add the ghost terms, Lagrangian, and so on. And when you add those Lagrangian, then your heat kernel become non-minimal. Because if you remember, we start with this kind of thing, but for the ghost action and that part, you will have derivative involved interaction part. And that we have recently learned and used in one case, but it will take some time to complete that part. Yeah, but it is yet to be done.
And how do you treat the Farman, the physical Farman field, let's say, which actually has an interpretation, let's say it can be like some connected to some physical particle. On the other hand, the ghost field, yes.
Yes, the gauge field, yes. For the gauge field, we have to
No, not the gauge field. I'm saying there are two different kind of let's say Grassmannian fields, right? One is for that represent physical Farmans, physical spin-up particle. Other represent, let's say, the ghost field, right? I think they're called degenerate Farman and non-degenerate Farman. If you use
so because the ghosts are basically
the treatment is different, or you also have to bosonize the ghost field.
I don't need to worry about them because they are harmonic in nature, but the action is basically still bosonic.
Okay.
If you think about the ghost,
then the derivative is double derivative there.
Yes. Yeah. But this bosonization one has to do only for this pure fermion.
So no, the only problem was actually there was a first derivative and the eigenvalue would have been plus and minus.
Yes. We cannot use the heat kernel method unless the heat kernel method is applicable only for bosonic Lagrangian and after doing the Euclideans in the Euclidean field theory. Yeah. Yes. Okay. So yeah. So now, as I told you that, okay, so now if you have a non-linear spectrum, right? So then we cannot write down these decompositions. So then, but still I have this formula. So what I can do actually, I can calculate the heat kernels in the Fourier basis. So I can translate the whole, this heat kernel into Fourier modes, and from there I can calculate. So I'm just giving an idea that this is existing literature. So now if because these are not the regular field theory that everybody encounters, but if someone is interested, then we can talk later about more on this thing, because this may take separate timeline for it. But what I'm trying to emphasize that, yeah, it is possible that even for the non-degenerate spectrum, one can calculate, but not in a regular way, but in a Fourier modes, one has to go and in a cascade way of doing that thing. But the beautiful aspect of this construction is that once you write down the effective action, the effective action equally again applicable for scalars and fermions, and because you have now non-degenerate particles, and some of the particles can be lighter also, right? So if you remember, the diagram that is still there in the back of board, that there are some in the loops, there are light particles and heavy particles, right? So then in the diagrammatic method and the function method, one has to calculate them separately, the non-local contribution, you have to remove them to get the local contribution. But what we do actually, this m square, we replace by some kind of lambda IR square. Okay, and then for the light particle masses, when that IR regulated, then what happens? If their IR regulated, then the Lagrangian that you'll be getting, they are not suffering from any kind of IR divergences. And then you just set mi to be 0, and then automatically all the loop contributions give you exactly the local ones. You don't need to calculate the non-local contribution and subtract them. So that's why this gives us two better handles to deal with. One is to the non-degenerate spectrum loop calculations, and also to deal with the light heavy mixing loops, and we can calculate directly the local contribution without calculating the non-local one. That is the beautiful aspect about that formula. Okay. So now a little bit so I don't have much to say. Okay, so there's one or two slides are left. So so what I'll end up with the giving the idea that this method is not only calculating for the the effective action, but also it gives a beautiful handle to calculate the EV divergences, the counter terms, and all those things. But this is a completely algebraic approach. What is the meaning of that? Let's try to recall what we do in the normal quantum field theory. So normal quantum field theory, let's focus on the scalar one. So scalar quantum field theory, even though we have interactions, when we calculate the propagator, we consider the free part. Our propagators are basically derived from the free propagator. That's why you call it free propagator. The Green's function of free propagators, right? 1 by p square minus m square. But then we draw the diagrams, we attach the external legs, and the external legs are designed based on what kind of interactions we have, and we draw all the possible diagrams with all possible this thing, and we calculate them to normalize the theory. But a lot of diagrams are there. But here we are not doing that thing. So what we are saying that, okay, instead of calculating the free propagator, I'll calculate interacting propagator. Now, how do I do that thing? That's a nice way that Green's function can be written in this interacting Green's function is written in terms of heat kernel integral as an interacting propagator. So if I integral with respect to t, the heat kernel, I'll get my Green's function. Now this Green's function can be expanded in the basis of these heat kernel coefficients. So these heat kernel coefficients are independent of each other. So they form kind of a vector space order by order, right? So then I can expand this heat kernel, Green's function in the basis of this heat kernel coefficient. And these are the, I will call the Green's coefficient Green's function, which is written in this particular form. And this is the modified Bessel functions, okay? And these quantities have the divergences. Now you might be wondering, okay, in the normal quantum field theory, we try to do some calculation of four-dimensional field theory, and then we go some analytic continuation and to d-dimension, and there we try to come back to again four-dimensional analytic continuation, then we get the divergences. But if you look into those things carefully, what is the actual weapon to extract the divergences? That is nothing but analytic continuation. The analytic continuation is a beautiful tool to extract the divergences. Even for if you do it carefully, you don't need to leave that dimension. So that means even if you work in a four-dimension theory, you do not need to go to d-dimension. You just calculate in a four-dimension divergences, and that's called the zeta function regularization. So here, if you calculate in a partitively the G0, G1, G2, those coefficients associated with B1, B2, B3, and so on, that can be written in this particular form up to order Z4. What is this? This is the x minus y. Now, what are the source of my divergence here? My source of divergence are x minus y tends to 0. That means when I'm taking the coincident limit, because remember, the heat kernel coefficient, if I calculate the coincidence limit, then it gives me the effective action. So I calculate this Green's function, okay? And then I know how to extract the divergences from them. But this is about the interacting Green's function. Now, with this interacting Green's function, what I'm supposed to do? I'm supposed to calculate my L loop modified Lagrangian. That means after L loop computation, I can get this effective action. And how do I read this thing? So this is basically my symmetry factor for any given loop. And this is the measure in the space-time. And these are my Bartes factors. And these are basically saying that how many Green's function are there. So G to the power P1, then P1 copies of G, Pn copies of another G on different space temporal and so on. This is a generic Lagrangian you can write down. Now, let's try to understand if I want to calculate a two-loop diagram. How do I do that thing? For two-loop computation, I need to calculate only 3 diagrams, and these are the vacuum diagrams. Okay. For any interacting theory in the scalar field theory, for example, let's say I have these 2 diagrams. Now I have only 3 propagators, and these are not free propagators, these are interacting propagators, and I have 2 such vertices. And recall that here there is no external legs are associated here, because these vertex factors and the Green's function capture all the interactions. So that's why I'll write down this diagram as in this particular form. I have 3 Green's function between x1 and x2. That's why I say gx1 x2 cube. I have 2 3-point vertex. I have v3 at x1 and v3 at x2. That's all. Another diagram is called the infinity diagram, where the 2 blobs are attached x1. Now you see that this is a one Green's function. There's another Green's function. So I have a g square, but both are at x1. So x1, x1. And then I have a 4-point vertex here. So I have a 4-point vertex here. And how do you calculate the vertex factors? In the same way, you take a function derivative of the Lagrangian with respect to fields. This is the pure 2-loop diagrams. But now I have an additional contribution, which is the 1-loop correction of the 1-loop counter term. So first you calculate the 1-loop process. From there you get the 1-loop effective action and the counter term. And that 1-loop correction of the 1-loop counter you calculate, right? So this is a one diagram here. Sorry, one propagator here, x1, that's a gx1, x1. And this is a vertex factor, but this is a counter term vertex factor. That means you have this 1-loop Lagrangian counter term, you take a function derivative of the counter term Lagrangian with respect to the field twice, and you get this vertex factor. So if you plug them, and then if you calculate, so Green's function, you know what was the form of the Green's function here, okay? And then we plug in back the vertex factor in this thing, and that will give me a beautiful result. So let me demonstrate with the simplest example. I think that will be helpful. So let's say consider scalar field theory with at equal to 4 space-time dimension in this particular form. So you can see I am not truncating my Lagrangian at phi 4, but also I am extending my Lagrangian to phi 6 operator. That means I'm interested in to calculate the higher dimension operator running also. So then my delta, this strong elliptic operator is basically del 12 by del phi 2 is this. So then this Lagrangian, if I take a derivative with respect to field twice, that is my u. This is my u. And then from my given formula, that big formula that I have written down, from there, I get this 1-loop effective action in this particular form. You just plug in back. So you know, and now you can see what the simplest way you can get the operators, right? You can get the phi 4 operator, you get the phi square operator, and the phi 6 operators. You just replace the u, you get that thing. So what I get the 1-loop effective action, and then you can see this is the counter term, because in the 1-loop level, you get the divergences with the order of 1 by epsilon. And then I calculate these diagrams. So this is the 2-loop diagrams. So then I can calculate my V3 and V4 for the given Lagrangian, which are like this. And this formula I had earlier, I plug it back. And if I do that, and manipulate, I get this formula from this contribution. Now, how to read that? There's a 1 by epsilon square, because that is what I expected. Because dimension 6 level, your maximum order of divergences, UV divergence would be 1 by epsilon square. And then you have a 1 by epsilon divergence also. But more importantly, if you do it carefully, then you will have this kind of term. What is the signature of this kind of term? This is the IR divergences. Because when you calculate the 1 by epsilon square, in the massless limit, there are some IR divergences. And the IR divergences appear of the order of 1 by epsilon square. So if you do not regulate your theory by the IR divergence, you would get a wrong UV counter term, because you cannot subtract the IR divergence from that. So to track that, you start with the UV IR regulator, and this M is behaving like an IR regulator here. So log M by epsilon is actually order of divergence as same as the 1 by epsilon square in the limit M tends to 0. So that's how we can extract out the IR divergence part from here, and we get nicely up to 2-loop divergences. Okay. And similarly, we play the same game with this diagram, and we can calculate this
So what is the
Yeah.
source of this IR divergence? Is there any massless particle?
No, the source of mass, if you put massless, then you cannot extract the IR divergence. Okay. So that's, sorry. Yeah. The source is basically in this theory, I can have a multiple M, right? Now, if some of the particles are lighter, that is the source.
Lighter, but still, if it is non-zero, then there should not be any
No,
IR
if,
divergence.
no. If it is not if it's not zero, then there is no IR divergence because the mass is the regulator. Okay.
Yeah.
But if the mass is zero, then you have to invoke a mass to start with. Otherwise, you cannot extract the IR divergences.
Okay.
So even the mass of the light particle is
And
zero.
then you see, if you take that parameter tends to zero, whether you recover some divergence.
Exactly. But if you set zero to start with, you cannot recover that part.
Okay.
Right. But
And just in the hit kernel method,
Hmm.
maybe 2 slides back.
This one?
Yeah, this one. So in this case, how do you this sum over n is basically this sum over number of independent solutions of this hit kernel?
No, this n is basically infinity because
Yeah.
it depends on where you truncate.
Yeah, I'm saying how to keep track of the perturbative order, means in coupling, let's say, in GXY. Normally, when we calculate the propagated in interacting theory, we keep track of the do it order by order, let's say, or at one loop or two loop, whatever you can think of as order. Okay. So how to keep track of that here actually?
No, here actually the one loop and two loop are decided by what kind of vacuum diagrams I'm computing.
Okay.
So that is tracked there. Okay. But within the two loop, where I'm truncating, that depends on
what is the diagrammatic connection between this method?
Okay, so diagrammatic connection is basically the expansion of G I can do up to infinite order. I don't worry about that part. Okay, the diagrammatic connection is following. So this is the two loop diagram, only these three. So if you calculate the full Feynman diagram approach, you calculate all the two loop diagram and get the result. That will be exactly same as this sum of the three results.
Okay. Now, just maybe slightly. So, if I want to calculate this tree diagram, let's but this is not propagator, right? This is vacuum.
No, these are the propagators.
We are calculating individual. So okay, what you are trying to calculate? I'm just a little confused.
I'm trying to calculate the Lagrangian.
Okay.
Okay, so let me tell you in this way. So in the normal quantum field theory, the way we regularize and the way we are regularizing here, they are different. Why? Because the normal quantum field theory, we do not regular. At the end of the day, we renormalize the Lagrangian, right? But the method is slightly different. We start with wave function renormalizations, coupling renormalization, and so on, right? And then we separately calculate them, and then we find out what is the term in the Lagrangian. We look in the individual term, okay? And in the individual term, we plug their wave function renormalization, coupling renormalization together, and that's the total contribution. Once we group, we say this is the renormalization. Sorry, this is the counter term for this operator, right? But here we don't need to do the wave function renormalizations and all those intermediate state. Here in this method, we are renormalizing the operator directly. That's why this is, straightforward. Okay. For example, in the QED, we have a coupling like psi bar, mu, gamma mu, psi. So, to renormalize this coupling, what we have to do? We have to draw the wave function renormalization for psi. So we calculate the z psi. We calculate the ZA from the two-point correction of the mu, right? Then we have this mu going to FF bar, and then there's an exchange of mu. So that will give me the correction to E. Then we put all this back in the bare fields in terms of the renormalized field in the psi bar mu psi term. So this is a combination of Z psi, ZA, and ZE. Then we use the wide entity to see what are they cancel among each other. But eventually, what we find out some quantity divided by epsilon, and we call it is a counter term of the operator psi bar gamma mu psi, right? Yes. I am saying we don't need to do that. Because we are dealing with the operators, I will give you the counter term of the psi bar gamma mu psi directly. Okay. Okay, I think that's what. Okay, let me go to the example. It will be more clear actually.
But then you'll be giving it also order by, for example.
Yes. Okay. There are two different kind of orders actually. One is
Exactly.
order, one is the coupling order.
Exactly.
So we are concerned the coupling, not the coupling order. Coupling can be any order.
Okay.
Because they are all weak coupling, right? Because that's how you can calculate the perturbation. But the presence of H bar tells you which order actually loop you are calculating.
Okay. So you'll be keeping track of that here.
Yes, exactly. I'll write down H bar explicitly and then I will see. And that's how actually I know that this corresponds to the two loop diagram.
Okay. Okay.
Okay.
Thank you.
Yeah. Any other question from other? Okay. So now let's see the example. So now you see, Sanjay, so as I was pointing out, that basically here the operators are basically phi d2 phi, the kinetic term of the scalar field, right? And then you have the mass term, you have a quartic term, and the phi 6 operator. But you will see we are not calculating the z psi or something, z phi, something like that. This is the one loop counter term we calculate, and then we calculate these two loop diagrams. But you see all the divergence is associated not with any individual field, but rather operator. So this is the counter term of this operator. This is the counter term of this operator, and so on. So we get the result of the counter term of the operator, not any field or something like that. We bypass that thing completely. Okay. And now this is a very important check, that if you have IR divergences you trace out, then if you add these three contributions, for example, the previous two and the counter term diagram, and if you add them, this blue color term should drop out from the total counter term, because IR divergence is not renormalized. If you calculate all the diagrams, that should drop out. And that's why even if you use the IR regulator, your physical quantities will not depend on the regulator. Okay, so that is the one of the cross check that you have computed all the diagrams in a correct way. Fine. So now what we are doing, we write down the full effective action Lagrangian by sum of this counter term Lagrangian plus this counter term Lagrangian and this counter Lagrangian. If you add them, what you find out the counter term of the operators. So you write down directly the counter term of the operators. But now you find out, okay, these are the counter term of the operators, that's fine. But I did not have this operator to start with. Then how come I have this counter term? So to deal with that, what you do, you use the equation of motion. d2 phi equal to this, and you plug in back. And if you use that, then you find out only those operators have the divergences associated with them with whom you started with. And that is what you expect, right? So this is the total counter term for individual operators. And now if you know the counter terms, okay, you can write down directly the, this thing, the beta functions. Because now you don't need to calculate separately. Even at the one loop level, the counter terms are the beta coefficients. Two loop level, you have to do a little bit of algebra, and you can, from the counter term, you can calculate the beta functions or the anomalous dimension matrix for the higher dimension operator directly. So now the beautiful aspect is that it is not restricted for the renormalizable part only. It gives you counter term for the higher dimension operators. This method can be extended for the Feynmanic field theory, and when the interactions you have a higher derivative operators, for example, if you have additional terms like in the Lagrangian phi 4 d2 kind of operator and so on, then also this method is equally useful and one can compute this thing. So this is one of the interesting method to calculate the beta function of the renormalize the theory and so on. Yeah, up to this part, any question? Okay, so I hope I have given you basically the idea of this modern tool about the heat kernels. Now, if it excites you, then of course you are welcome to write to me and to learn more about that thing, because this is basically paving the direction to an algebraic approach of the quantum field theory. So now we are in the last slide. So where we are saying that these are the take-home message, that effective field theory you have learned that it connects physics of different scales. Okay, it's a very effective tool, especially when new physics is unknown. And we have learned about the top-down and bottom-up approach, and these are two complementary aspects of effective field theory. And we should be able to, use effectively more efficient way if you take on board both the methods. The defined UV theories can be brought into the same footing on this, which is called the effective standard effective field theory, where we can perform a comparative analysis among these different kind of theories. And we have seen that if we use the electric equation observers and the Higgs observers, that will be helpful to understand the the status of these theoretical prescriptions that are floating around us. The circumhalations could be game changer because it's a very interesting consequences are given for depending on the for the whether it's a extension is scalars or fermions, and higher order calculations beyond one loop and the RGs are playing crucial roles. It's important. It's good time to invest some time to design the methodologies to compute them in a sustainable way and consistent way. Okay, so I think this is what I plan to tell you, and yeah, so that's all. And thank you all for your attention and tolerating this torture for last 5 years. Yeah.
Yeah. Thanks a lot, Jyoti. Let's first take some question if there are any, and then hello, if you have any questions or comments, you can ask on any of the 5 lectures, not only from today's lecture.
Sorry.
I'm asking the others. I am asking
Yeah,
others whether they have any question over the last 5 days lectures.
Yeah. So any question from these last 5 lectures, or if you have any generic thing you want to know about the effective field theory, just feel free to ask me.
Oh, okay. So anyway, we'll have these lecture videos uploaded we'll have them uploaded today maybe, and we'll share with you, and also I'll share the slides. Maybe some of you can look at them again, and if you have any question, I will be very happy to answer them.
Of course, yeah.
Or email also.
Yeah.
Okay, so let's thanks Jyoti for this exciting lectures over the last 5 days. And if you find it difficult, that also you should then appreciate the level of work that they're doing. So it's better that you find it difficult also in that sense. Okay. Anyway, you can. I hope there'll be a lot of questions later on once you try to go through them more carefully. Okay, even we have more questions, but we have to understand some details also. Okay. So okay, yeah. So this actually may be for us it's a kind of introductory thing, but unless we work.
Yeah, actually, I am pretty much personally excited about this heat kernel because, as I was telling Sanjoy, that this actually opens a completely new way to calculate the quantum field theory. Okay, so and it's a giving like for example, temperatures and the non-equilibrium quantum field theory and like Swinger-Keldy's and all those things. There's so many things one can do actually. So yeah, so there are a lot of things to do, but yeah, let's see.
Okay, so we then stop here with a big round of
I think there's a question. Let me see. There's a message.
No, I think there's a thanks.
Subhajit. Okay. Thank you, Subhajit. Subhajit, I'll write back to you. I received your email. Next week, I'll write back to you.
Okay, sir. Thank you.
Okay. Okay, then. So
okay, thank you, Pradeep. Yeah.
Yeah.
You can maybe stop the recording as well.
Yeah.